or somebody's on the highway 5 miles over. That it doesn't seem as much over as when they're going slower. So you got to think about percent changes. But most people would not, I just had to get that in there for the video. Most people would not write a ticket within this range. So if we want to talk about, and they say the speed limit 65, that's okay. What's the probability that the car stopped or ran will be traveling faster than the speed limit? So anything over 65. Now, throw my situation on the back burner for a moment. Doesn't matter whether or not they would get a ticket. What's the probability that a cop on this road would, like, radar somebody speeding? Not that they would pull them over, but that they would radar somebody who is speeding. Well, how many total people had gone past is the first thing you want to ask yourself. What's that?
50.
You already calculated it? Then, how many people are speeding, Emily? Well, yeah, I know.
No, I can't see that far.
Oh, it's on your paper, too. Ben, are you getting fired, dude?
Okay, I gave
Benjamin, what have you done?
Unless she accidentally put it away with her other stuff.
I don't think I
there's
did.
normally one
Possibility.
extra.
And I sent these to the copy center, and there still should be.
There's not.
Weird.
Seth, did you give me one? Yeah, see?
You did put it away with your other stuff?
Hi, you can't blame me. What?
Ben, you should have reminded her not to put it away. You're still fired.
All right. So, as Emily gets her notes back up, there's 13 people speeding. So, if we took the 13 over 50, we do not need a calculator for this. How do I figure out what percent or what the probability? Because probability is not in percent form. Leon, your hand was up first.
2 over 2.
Do what?
Multiply by 2 over 2.
Yeah, double the top and the bottom, multiply by 2 over 2. We get 26 hundredths, which can be rewritten as 26 hundredths. Or if we wanted to look at it in percent form, we can. But when we discuss probability, probability is out of 1. So we're all talking about chances out of 1. So when he radars one car, what's the probability that car will be speeding? 0.26. Then we can talk about percents. What is the percent chance he would find a speeder? That'd be 26%. But probability is on a scale of 0 to 1. 0 being completely impossible, 1 being absolutely certain.
Have you done the speeding ticket?
Yes, it is not fun. I was driving to Florida for my niece's Make-A-Wish trip. We were going down to Disney, and I had my Jeep, which had bigger tires on it than stock. And we'll actually do this a little bit later in the year to compute what difference does that make. Because your computer is set to rotate one tire spin goes one certain distance, the circumference. When you get bigger tires, you're traveling a faster distance or like a further distance in one rotation. So although my speedometer said like 65 or whatever, I was actually traveling at like 73 because the wheels were like off-road tires that were made bigger, really knobby. So yeah, got that. And actually, we were both coming downhill. So then he caught me, he turned around, he caught back up to me, he pulled me over. So when I realized I'm getting a ticket, this is happening, you are fully within your rights to ask to see the speedometer, like his radar, because I didn't believe that I was going that fast. I was like, dude, I looked at my speedometer when I saw you, because I saw you, like I was not going that fast. And that's when I figured out how off the tires made me. And I walked back to his car, and I was like, excuse me, officer, weren't you speeding also? It's funny how that doesn't matter. He's like, well, I was going downhill. And I was like, well, I was going downhill also, but okay.
Can we watch that one video?
No. So, relative frequency.
With the
Now, if we think back, to yesterday's lesson, what's the... I'll wait. Like, if it's important, I will wait. What's the real difference between experimental probability and theoretical probability?
Mr. Hudson, are you filming this?
Yes. What?
Experimental is like what did happen, and theoretical is what would happen.
Experimental is what we did do. Theoretical is based off what we know. Standard 52 card deck. What is my probability of drawing a heart? It's almost Valentine's Day. What's my probability of drawing a heart? theoretical. Ben?
Doesn't matter anymore what you said.
My bad.
Probably not loud enough for the video.
1/4.
1/4, right? Now I draw club, spade, heart, club, club, spade,
Where are the diamonds?
spade, heart. Yeah, right? So where are the diamonds? Like if there's one. So according to this, my experimental probability, what's my probability of drawing a diamond?
1/4.
Not my experimental. My experimental probability.
You just pulled 8 cards and got 2.
Yeah, but
No,
you only
you
got
counted wrong.
Diamond, I'm now asking. You
Oh.
pulled 8 cards and got 1 diamond.
Yeah, he pulled 9.
None.
You
Just
said
basic.
diamonds.
Yeah, he thought he didn't.
Get rid of one of these. We need a diamond. I need a diamond for this to work. So, theoretically, 1/4. Every suit has a 1/4 chance. But experimentally, when I just did it, came out to be 1/8. So experimental and theoretical probability is not always the same. You have to be very careful with what you are actually discussing. We can use theoretical probability all day long, but when you go and sit at the casino table, your theoretical probability doesn't matter when the cards keep coming up against you. If you've ever heard of counting
Yeah,
cards
Oh,
or
yes.
read the book Bringing Down the House or seen the movie 21, that all deals with probability. What's the probability of getting a low card versus getting a high card, which in blackjack is all that's important. Am I going to get a low number card or a high value card? That determines everything. So experimental versus theoretical gets very dangerous. That's a very good example of when theoretical probability doesn't work out. So, relative frequency is the frequency that something happens relative to the total amount of times that it could happen. So if we say, what is the relative frequency this year, experimental relative frequency of getting a snow day? None, right? We had a 0 chance experimental probability of getting a snow day. Now if we looked at last year, what would be the experimental probability then?
10 to 20%.
It'd be different, right? Because we take the days that we had for relative frequency, days that we had snow days, over total days, which is supposed to be 180, and we could figure it out that way. So survey results of a survey of students, music preferences organized in this frequency table. What is the relative frequency? I need to grab those notes so I know what you guys have or not. I think this is not done out because it's easier. When the content's easier, I don't always leave the problems done out for you guys. So, prefer rock music. First thing we do is find out what is the frequency of rock music. 10. So 10 is the group that I'm looking at. To find a relative frequency, it has to be relative to the total. So we need to total up. Is it 40?
40.
So I put my rock over my total. And I get 1/4 or, sorry, my brain was getting ahead of itself, 0.25. Or we could say 25%. Because we do use percents when we're discussing probability, but that's not technically how we're supposed to do it. Discussing on a scale of 0 to 1. So try the got it for classical music. Like EDM maybe, or the genres that aren't necessarily categorized by one of those.
Is it? You choose rock, right?
Yeah, rock or alternative. Could be alternative rock. But there are kind of new musical categories that did not exist before, like indie and those sorts of things. So we look at classical over my total. What'd you get, Seth? So you did 5 over the 40, which then reduced to the 1/8, which as a decimal, yeah, 0.125. If you guys have not yet remembered that an eighth is 0.125, here's another, my brain works in weird ways. Another way that you can remember it is 1, 2, and 5 add up to 8. So 0.125 is your 1/8.
But 0.25 doesn't equal.
I know, it doesn't work in all situations. I'm just saying that's one way to remember that specific occurrence. 1/6 is 0.16 forever, but that's just cool. 0.1 forever, because anything over a 9.
2 squared equals 4.
2 times 2 is equal to 4.
But wait, 2 times 2 is equal to 2 plus 2, so is 3 times 3 equal to 3 plus 3?
No.
Always a good.
Plus
What did
2
you just say?
squared.
Alright, try this. A student, say we're doing science fair or something like that. Student is collecting data, tossing 3 coins one after another. Could be the same coin, could be different coins, doesn't matter. Using the results below, what is the probability that exactly 2 heads will occur in the next 3 tosses? If you were to think about this theoretically, what's the probability of 2 heads occurring in 3 tosses? Only 2 heads, right? So what probability does each head have? 1/2. So it'd be 1/2 times another 1/2. But then I'd have to have a tails, so it'd be times another 1/2. So it'd be half of a half of a half. But that's theoretically. Let's see experimentally. Where does he have exactly 2 heads? Well, right here, and right here, and right here. So we've got 7 plus 6 plus 2 gives me 15. What's the total of all tosses?
Oh, never mind. 6. I got it.
12, 38, 48, 50.
No.
So we take our 15 over 50.
3
5 by
tenths.
5.
Yeah, so we can either simplify down to 3/10 or we can multiply up into 30 hundredths. Either way, we'll get 0.3 or about 30%. So when we think about our experimental, the other thing is we thought only about give me a heads, and a tails, but there's also the situations that could have been heads, heads, or tails, heads. So that increases your probability because you didn't say 2 heads, then a tail. We just said exactly 2 tails. So that's when the specifics of the situation get really important to say what you want to happen when. And this gets into the argumentation of combinatorics and permutations and all that sort of stuff of what about if we replace it. Coin tossing never matters because we always have heads or tails as the outcome. But if you're like drawing things with or without replacement, changes the probability a lot. We will get into, I think we'd get into that a little bit in this chapter, with or without replacement situations. What would you expect each of these probabilities to come out to be? If you did theoretical probability for spinning a 1, a 2, a 3, or a 4, what would you expect, Seth? A 4th, right? Is that what we see based off this table? Are they all evenly distributed? No. So as we see in experiments, things don't always work out as we anticipate. Question or
Can
answer?
I do it?
Sure.
You have 18 over 100.
So I'm going to get into proper notation now. We're going to say probability of spinning a 4. So P of 4, Ben is saying is 18 over,
100.
it's 100 total.
Yeah, which then just equals 0.18 or 18%.
So is our 4 underperforming or overperforming? Underperforming. And the law of large numbers tells me what? Who knows the law of large numbers? It has to do with this. Let's say I spin the spinner another 100 times. Would I expect the 4 to still be underperforming, or would I expect it to do better next time?
Better.
Seth?
We don't really know. It's random.
But according to the law of large numbers, I agree with you that we don't know. there's really nothing that impacts it. But according to the law of large numbers, yeah, according to the law of large numbers, it would actually start overperforming. Because what the law of large numbers states is that all probability, I mean, I'm simplifying it down, but all probability will work towards the theoretical probability. So if I have a quarter and I flip it 5 times, and I get 5 heads, that doesn't mean I have a magical quarter. That just means I just got 5 heads in a row. But eventually, there will probably also be an instance of 5 tails in a row. And eventually, there will probably be an instance of heads, tails, heads, tails, heads, tails, heads, tails. The law of large numbers says that eventually I'll even out to half heads and half tails.
Are we assuming that the spinner is on a flat ground?
Yeah, we're assuming it's fair, it's even, it's, yeah.
I mean, if it was tilted, that makes sense.
Yeah, if it was tilted away from the 4,
I mean, 3 and 4
you stink.
are both pretty low compared to the. What? I can see that happening.
I'm just going to pull up the notes. Can I get away with the Zoom? Yeah, we're close.
Mr. Johnson, next up is Mr. Paul. He was the quarter.
Yeah.
We had to draw from.
Huh? I've not. He has not come to talk to me. He totally can whenever he wants to. Alright, we need to now fill in our table here with the frequency and then the probability relative to this situation. Recent competition, 50 archers shot 6 arrows at a target. 3 archers had no bullseyes, 5 hit 1 bullseye, 7 hit 2, 7 hit 3, 11 hit 4, 10 hit 5, and 7 hit 6. What is the probability distribution for the number of bullseyes hit for each archer? So, I'm going to fill in our table.
Is this all experimental?
Yeah. There's really not a good way to theoretically predict bullseyes hit. Because it's not like we're rolling a die or or anything like that. I was about to say rolling a dice. Huh?
This is theoretical?
No, this is all experimental. He asked, is this all experimental? I said there's really no good way to theoretically predict this because it's not like there's a certain number of outcomes that always have to happen eventually. Like, nobody could hit a bullseye. It doesn't have to happen. So, 3 archers hit none. 5 hit 1. What's your question,
7,
bud?
7, 11, 10, 7.
Isn't it like out of 300?
For archery? I'm not certain how the scoring goes for that.
No.
Yeah.
We shoot 5. We shoot 5.
No, because I meant 50 archers shoot 6 arrows, so isn't it out of 300?
So, that's the question. Because they hit the target other places, but no bullseyes.
Yeah, might have missed they should not be archers then.
So, we need to look at what frequency are we dealing. What is this frequency? What is the 3? What is the 5? What is the 7? Because those are not arrows. You're thinking of arrows. So I like your thinking because if we were given the frequency in arrows, then it would be out of 300. But what is the frequency being given to me in?
Like Emily said, the people out of 50.
Archers, right? How many archers? 3 archers, 7 archers, 7 archers, 11, 10. So since these are archers, we need that to be out of 50 to determine the probability. Yeah?
Yeah, when we're doing the probability, do you want us to do percent?
No, we want to do it in decimal form.
Okay.
So since these are all out of 50, we can really just double it and put it in decimal form. Is that what you're going to say, Grant?
Yeah.
So what do you get for this one?
0.06.
What do you get for this?
0.14.
Yep.
0.14. 0.22. 0.2. 0.14.
Good job, Grant.
Yeah, good job.
So what is most probable in this competition to happen? What is most probable to happen, Ben? 4 bullseyes. An archer hitting 4 bullseyes is the most probable thing. What's the least probable thing? Grant?
Hitting 0 bullseye.
Yeah, which we would expect because, like Emily said, if they're a professional archer, they should not be hitting 0 bullseyes. That should be the least probable thing. Well, it's an archery contest, so I would assume that they're at least trained.
Well, actually, I think if
Okay,
you don't have to hit the
Billy,
bullseye,
why are
if
you
you
gonna
hit
do it
around
for-
there and you're just super fast.
Oops, I just closed my eyes.
Yeah, I don't know how all that is structured. So always think about what Greg was saying. How do we figure out the total?
That's what. Oh my.
On a math test, last question, then time for homework. On a math test, there were 10 scores between 90 and 100, 12 scores between 80 and 89, 15 between 70 and 79, 8 between 60 and 69, and 2 scores below 60. Essentially, they did a 10-point grade scale, A, B, C, D, E, and failing. What is the probability distribution for the test scores? So we first need to figure out our... Oh, my bad. E, a couple grades that I was in, they used E instead of F. Because they said using F was wrong. If we go down A, B, C, D. Yeah. But now we use E for example. What does B stand for? You know, like, there is...
Bravo!
It's brilliant.
No,
So
B
what does
stands
C
for
stand
crap.
for?
Cowardly.
And D?
No.
Don't even try.
We don't need to say
Dipstick.
that word.
Dipstick.
So, although we don't like letter grading, I'm going to categorize this in a table with 10-point letter grade scale.
Aren't there like 47? Okay, I didn't know if I counted right.
So, 10 of these people would have gotten A's, 12 would have gotten B's,
Brilliant.
15 would have gotten C's,
Skids.
8 would have gotten D's,
Dipsticks.
and 2 would have been failing or worse.
How's fat essentially yeah, failure.
Dude, that's what.
So, how many total tests were taken? 47. So to find the probability distribution, we're now going to say the probability of an A, the probability of a B, the probability of a C, probability of a D.
Didn't finish the B.
What?
Courage. Cowardly.
Mackenzie? Yeah.
22, 0.26, 0.32, 0.97,
Point what?
Yeah.
What is the most likely grade up here? Greg?
Cowardly.
Cowardly. A C is our most likely grade. Now, if we want to look at above a certain grade, though, how many students scored a B or above? Well, that'd be 47%, which is pretty good. How many students scored a C or above? That would now be 81%, I think, or no, 79. Yeah, if we add all those up. So then you can talk about, you know, the different ranges and where kids are falling and things like that. Is relative frequency making sense? Yeah, you learn basic like frequencies and things like that. Not kindergarten, obviously. Because you totally knew how to design.
Leah, you still don't know how to divide.
Yeah, I did not get to those. I'll get those back to you tomorrow. Dude, I had so much to grade. I'm actually probably gonna do them like right now.
Only a certain range of bad.
Sure.
Okay, Phil, and you passed that. You passed that by a lot.
I passed it by 0.2%.
You passed it by no.
Wait, that means I'm on fine.
Hey guys,
You're very much on.
can we try to show me that you actually care about this time and you want to do your homework?
Yeah.
That would be delightful.
Okay.
Whoa. Wait,
what's relevant